borehole at this station. So it has really good long period noise characteristics that I'll show you. It also has a post hole, which is a much shallower sensor. And here, I'm getting a message there. Let me get rid of that message. Here we can compare VH and LH channels. The top two in this view are this KAPI station, a BHZ, and a long period LHZ channel that you can see, and they're both fairly quiet. This is a deep borehole, about 100 meters depth, so you can see the most of the PSDs occur very close to the low noise model, that lower gray line that we talked about in the previous lecture. There's some funny features in there, some spikes higher up, but for the most part, this is a good quiet station. To the upper right, that's the long period vertical channel, that's LHZ. And what you can see there is there's a real strong bimodal distribution. And that's due to a sensor change that occurred in 2018. So you can pull out some fairly interesting information. You can see the difference in the long period noise levels of the Geotech KS54000 sensor, which is that higher noise level, compared to the new Nanometrics Trillium 360. Again, these are both borehole sensors, 100 meters down in a hole. And you can see that just the sensor alone, by doing the new Nanometrics sensor, you can improve the noise levels at the long periods by as much as maybe 20 decibels or so. And that's important for, getting into long period, using the long period data for surface wave studies, global tomography studies, or earthquake products like finite faults and moment tensors and things like that. Below that, the panels below, those are the BHZ and the LHZ components for the post hole sensor at that same site. It's a Nanometrics Trillium 120 sensor that's about 2 meters in the ground, much shallower. But what's interesting is that they look very similar. So the 2 meter post hole has very similar noise characteristics to the borehole, which is interesting because that means you can achieve very good noise characteristics with a much cheaper installation, a 2 meter borehole post hole as opposed to a 100 meter borehole. So the post holes have become quite popular in the United States and Canada. Because of that reason, you can get really good long period noise characteristics with a relatively cheap installation. Those are the vertical components. The next screen I'll show you. Let's see, having troubles advancing here. Here we go. This is the same station, same setup. The top two are the borehole BH and LH channels, but these are horizontals. And so you can see a little bit more higher noise in the horizontals at the long periods, a little more variation. But still, what's interesting here is that you really don't see much difference between the 100 meter borehole and the 2 meter post hole. Again, suggesting that you can get to pretty good noise levels with a shallowly buried post hole sensor. Okay. Again, it's a Nanometrics Trillium 360. That means the long period corner is at 360 seconds. And then the post hole sensor is a Nanometrics Trillium 120, which has a long period corner at only 120 seconds. So again, that's pretty good, pretty good comparison. Surprising, actually. I thought the borehole would show much better long period noise characteristics, but they're very comparable.
So how do you explain it?
I think it gets down, once you get below the surface, maybe 2 meters, or you really do stabilize the sensor. It's also well insulated. And so you really don't have to go too deep to get pretty good noise characteristics out of, and that's kind of like I mentioned, these are becoming quite popular. A lot of the US National Network ANSS stations are going to post holes, and the Canadian National Network are experimenting with post holes. And that's because you can get really good noise characteristics for a relatively cheap installation. Okay.
Thank you.
Yeah. In the last session, there was a question about strong motion. So I wanted to show at this very same station, KAPI in Indonesia, there is a strong motion sensor at the surface. It's a Kinemetrics epicensor. That would be the bottom panel. And the top panel is a comparison with the borehole Bhz component. I just wanted to show, I mentioned in the previous lecture about how the strong motion sensors have a very high noise floor. So what you can see is that bottom panel, all of the, most of the PSDs are at a very high level, well above the high noise model. That's because the sensor, the strong motion sensor, is so insensitive that you really cannot detect anything below that sensor noise floor. The point of these sensors is to record strong motion on scale, of course. And so what you sacrifice with that is the ability to detect small earthquakes, and also to detect the ambient noise conditions of the earth. You really cannot see ambient noise. You can only see the noise floor of the sensor. And if you look at above that, and sort of the minus, 70 and up range, you can see very faint pink lines through there. And those would be earthquakes that pop up above the noise floor of the strong motion sensor. Those are probably fairly large earthquakes, probably magnitude 5, magnitude 6 earthquakes within a few hundred kilometers. You have to have fairly strong motion to see it, to record above the noise floor of the sensor. So there, I just wanted to show a comparison. We can do a lot more of looking at detail of the sensors and the stations on the next lecture. But I just wanted to show a comparison with a strong motion because of the question in the previous lecture. Okay. And again, since it's a little more informal tonight, if anybody has a question, please chime in or let me know somehow while I'm talking. Okay, if you'd like. One thing I wanted to note too is these have quite a lot of data. You can see the date range is from 2015 to 2021. So this is almost 6 years of data in these plots that you can see. So that's one advantage of these plots that I don't know that I really mentioned in the previous lectures, just how much data you can have available in one single view. And so that it really gives you a good sense of the behavior of your station. Okay. Here's another nearby site. This is Cocos Islands, which would be to the southwest of Indonesia. This is a South Pacific island station operated by the IRIS-IDA Global Seismograph Network. And this is one of the noisiest stations in the world, really. It was probably used to define the high noise model. If you look to the upper right, the PDF plot in the upper right, you can see that most of the PSDs in that plot are pretty much go along the high noise model, at least at the short periods. That's the vertical. The upper right is the vertical component, the Bhz component. The lower right is a horizontal component. And again, you can see even at the long periods, it's mostly at the high noise model. And I think if you remember, I mentioned in the previous lecture that the high noise model was defined by island stations, mostly in the South Pacific. So this was one of the stations used to define the high noise model. And you can see the black line or the mode of the distribution pretty much follows the high noise model. So look again, moving, we can do the same kind of comparison. There's a 100-meter borehole sensor with a installation with a Nanometrics Trillium 360 again. And then below that is the 2-meter post hole with a Nanometrics Trillium 120. Very similar setup as the KAPI sensor station that I showed previously. And here you can see a little bit better, a little bit more improved noise characteristics, but not much. Really, the post hole does a pretty good job of mimicking the deep borehole sensor. So you really do get pretty good noise characteristics with these shallow post holes. And I've been looking at some of your sites as well, the geophone sites, and I think that would be a pretty good recommendation to consider if you want to improve the noise characteristics of some of the stations in Indonesia. I'll show you some examples as we move forward. So this is the Mustang. Here's the Coco. Let's see, what did I just do? Okay, here's the horizontal examples of the horizontals, just like before. You can see the borehole has, if you look in the upper right hand corner, you see that for some frequencies between 10 and 100 seconds period, the borehole does have lower noise characteristics, so it does a little bit better job, but it really doesn't do that much better than the post hole. So again, that's a good thing to consider. Again, this is about 6 years worth of data that we're looking at here. It's quite a bit. So you really see the overall characteristics of the station when you look at this much data. You don't always have to look at this much, but it does give you a good sense of how the station's performing. So let me get out of that for a second and just show you how that would work. If you can still see my screen, this is the PDF noise PDF Mustang site. So you can see it's just, here's the URL. You really just have to do a Google search and you'll find it. But you can select, let's select another one. Here's a station up in Sri Lanka, I believe, PALK. Let's select the BHZ component. And what it does down below here is it creates a URL that you can just click on. Is everyone seeing my screen?
Not yet.
Okay. Yes?
The screen is a previous slide in my screen. We can see the previous slide, but not now.
Okay. So you can't see the website that I'm on?
Yes, we cannot see the website you talk about.
Yeah, okay, I don't see it either on my screen, so stop share, and share again. How about now? Can you see it? No?
Yes, we can see.
Yes, okay.
We can see in the web.
Okay, so here we go. So again, here we are. This is the Mustang website. Is anybody familiar
Can
with
you
this?
maximize, sir?
Yes. Like this. So what you can do is it creates a URL down here that when you enter the information into this dialog box here, it creates a URL that you can click on, and then it will produce the plot based on the information that you selected. There's PALK. Let's see, there's another, if we go here. Here's another interesting thing. This is the metadata aggregator, and you can look at all kinds of different networks. So this station here, PALK, is what I was just looking at. This station in Sri Lanka, PLAK. And so,
That's a very quiet station.
yes, it is. So here's the, yep, this is the PDF that's produced by entering the information in here. We can change it. Let's look at the LH. We can pull up the long period channel and you can look at it. So this might be useful for you to just compare some of your stations versus other stations in the region. As Walter just noted, this is a very quiet station. This is the LHZ channel, and you can see that for the most part, at the very long periods out by a 100-second period, the PSDs are very near the low noise model. So it's a very nice station. Okay. So let's go back to this. Okay, you should be able to see my presentation again. So let's move on. That's Mustang. Has anybody used Mustang? Are you familiar with it at all? Is it a new thing?
Yeah, I think not yet. We use the Mustang.
Not yet?
Yeah.
In the past, Tim Ahern and another person came from Iris to Jakarta and gave a week-long course that included Mustang.
Okay.
Yeah. Mm-hmm.
That was of course, that was 2 years ago.
Okay. Again, it does not have your network in it, and it doesn't have the geophone network, but it does have other stations that might be useful to look at. Okay, the next software system that I'll talk about is PQLX, and this is a system that was developed by Iris and Usgs. It's not web-based, it's more of a standalone system, and it's meant to be used by a QC analyst or a field engineer that's out in the field looking at their data, looking for quality control issues. And it's quite useful. It's interactive. It has a number of different features. I can go through some of them. I can give a demo possibly next week. Not really prepared to do that tonight, but I'll just show you some of the features tonight. But it's again, it's interactive. It's open source. It's quite old now. The last version was in 2011. So there's now a new commercial version called SQLX that I believe you guys have a site license from Nanometrics. Does anybody know, or does anybody use that, or can talk about how it's used?
Yeah, maybe someone from the instrumentation division already use SQLX because they have the license.
Okay, so no one here tonight?
Yeah.
Okay.
But actually, what is the differences between the commercial version and the free version, or SQLX and PQLX?
The commercial version, well, here, let me move forward. So PQLX, the open source version, again, it's quite old. The last version was in 2011. It requires you to pre-install PQL, which is the like a waveform viewing tool developed by Iris. And it also requires installation of an SQL, the MySQL database system. It uses a database to store all of the PSDs. The new commercial version does that all automatically. You download an installation package through Docker, and it does it all automatically. And there are a bunch of bug fixes and updates that have been done in the last 10 years or so. I do think the open source version still runs on Linux, and I wasn't able to get it to run on a Mac in the last couple of years, but I think it still runs on Linux. But it's now, again, 10 years old, so it's hard to know if it's really useful, if it can run on modern operating systems. It requires X Windows and things like that, sort of standard old style X Windows program. So yeah, it's still available. The website here is the download is available through Iris. If you just Google search it, you can find it. And I'd be glad to help with that if anybody wants to do it. But the installation is quite intensive, so I didn't really want to go through that tonight. There's a user's manual that I wrote with Richard Bose, who's the principal developer. That's available through the USGS. It's an open file report. You can just search PQLX USGS open file report and you'll find this. You can get the PDF. It runs through all of the installation procedures, all the requirements. So that's available through the USGS website. And again, I'll make this PowerPoint available, so all this information will be available if you're interested. Okay, and so that'll go through. It goes through some examples and how to basically all the different functions of the software. There are a number of cool things. Let's see. Let's move on to the SQLX version now. There are a number of interesting views that you can have. This is the main screen where you can look at all kinds of many different stations. These are geophone stations that I have been processing the last week or two. You can see the very top row is station GSI 3.
Tadi di chat juga saya tulis nih, saya dibantu Mas Yanuar gitu ya.
I'm sorry,
Okay.
say that again.
Oh ya.
Can you see that? GSI.
Thank you.
There's the east, north, and vertical component along the top. The second row is JAGI, which is in the southern part of the North Island, I believe. We can look at a map if necessary. But this is, again, it's updated from PQLX. It's much simpler installation package. It has all kinds of different views, and I can show you some examples. It just has this general view. You can load in all your stations. You can flip through them. It's quite handy if you're a QC analyst and you want to look for, see how well the stations are behaving. You can flip through quite quickly and look at your data. The bottom row there is station LHMI, 3 different components of motion. You can see they're all very good. The vertical, the right side is the vertical, and you can see the vertical channels all look very nice. They're very low noise at near the low noise model. The other channels, though, the BHE and the BHN channels, you can see the long period noise never really settles out. You can see there's a lot of smearing. You don't really get into the bluish colors. It doesn't really stabilize. The long periods look fairly unstable, which usually suggests that there's a lot of, that the vaults are quite shallow and there's a lot of thermal variation. Heating and cooling can cause tilt of the sensor vault. And so that's what happens there when you see that long period, that smearing in the long period. Okay. I'll go through and show a couple other examples. Here's a view where you can look at diurnal variations or variations by hour of the day. This is again station GSI, the BHE, BHN, and BHZ components. And what I've done, this is almost 3 years of data, starting in January 2019 all the way to September 11th, which was just last week, I believe. And what I've done is I've taken all of these, there's 44,400, 500 some hourly PSDs in these PDF plots. That's a lot of data. So what I've done is to the panels to the right are I've taken and binned them by hour of the day. and computed the average of each hour. So in that plot, you can see the variations throughout the day. For example, the upper right panel shows very strong diurnal variation in the long periods. You see the blue band from about maybe 20 to 100 seconds period. You can see this is in UTC, so hour 0 is about what, 6 a.m. your time, I believe, in Jakarta. So what you can see here in this upper right plot is considerable variation in amplitude throughout the day. During the daytime, you get the green colors, which indicate high noise levels. And then at night, it lowers down to the blue colors. So again, that's a lot of variation throughout the day, probably because of heating and cooling, sun on the vaults. And then when the sun goes down, it stabilizes a little bit more. So you can see that really strongly in the two horizontal components, BHE and BHN, at this particular station. You can also see it, well, let's look at the vertical too. The vertical at long periods is a lot more stable. You can see in the lower left panel, the PDF, you can see that it really stabilizes out and you get brighter colors, suggesting higher probability that it's staying at a nice stable level more often. And then when you look at the diurnal plot in the lower right panel, you can see there's very little variability by hour of the day. There's just a little bit of increase noise during the day and the early hours, but not too much variation. If we look at the short periods, at the bottom, let's see, that would be the left side of the PDF plots. On the left side, you can see the noise is quite high, gets up towards the high noise model on all three components. And you can see there's a lot of variability through the day. If you look at the right side panels, at the short periods, 0.1 seconds roughly, which is about 10 hertz, you can see the red band changes quite a bit by hour of the day. Again, very similar to the long period, you get higher noise levels in red during the working hours of the day, the hours when everybody's awake and driving around. And then in the evening time, in the nighttime, the noise levels at the high frequencies or short periods drop down quite a bit to the green colors. Is this station, well, generally at these frequencies at sort of 9 to 10 hertz, 0.1 seconds, this is cultural noise that's related to human activity. So I would bet that this station is near a road or near a town or a city with a lot of activity. Does anybody know where this sensor is located? Is it located in a city or close to one?
In Nias Island.
Nias Island? Is it
Yes.
heavily populated or?
No, it's offshore of Sumatra, south of Sumatra.
Yeah, I just wonder, it does have this variation in the cultural noise. So I just wondered if there was a town nearby or a road nearby. Could be a road. Anyway, that's what you can see here. You can see that in the PDF plot. If you look at the upper left PDF plot at the short periods, you can see there's kind of a bimodal distribution. You can see two distinct levels of noise. The higher level is during the day, as you can see here, and then the lower level is at night. And you can see that in this hourly diurnal variation plot pretty well. So again, SQLX, PQLX, pretty useful. It has these views where you can learn a lot about the behavior of your sensor, okay? Here's another example, the same station, GSI, and instead of binning by hour, what I've done is I've binned, what the software will do is it'll bin by month of the year. And so, again, the left side of this screen are the same PSD PDF plots that we saw in the previous slide. But again, instead of hourly, we're looking at monthly binning. So what you can see here is in the upper right-hand panel, at a period of about 10 seconds, you can see a pretty strong seasonal variation where you have the highest powers, highest noise levels occurring from about April to October, November. And then and then it quiets down a little bit in December, January, February, March. And so that is the microseism that we discussed a lot in the previous lecture. And so it looks like that's probably related to just seasonal storms out in the ocean. The more of storms are occurring in the southern hemisphere winter, probably, just like they do in the northern hemisphere. Up here for us, the winter time is when you get most of the storms. So for you guys, from April to October, you get much higher microseism noise, but then that dies down in December, January, and February. Okay. So again, I just wanted to show some of the different types of views you can get in SQLX and how you can learn about the variation of your noise levels in your data. Okay. Another interesting view that you can do with PQLX is you can take it to something called the detail screen. So let's go back one. See, this in the lower left panel, the PDF that's the vertical component, BHZ, and you see there's a slight little few PSDs that clip across the top of the low noise model. Those are probably not real. That's probably an indication of an instrument problem. And so what you can do is if you click on that panel in SQLX, it'll take you to a detail screen where you can, if you look at the upper left panel, I've drawn a little box around those individual PSDs, isolated them. And then the lower right panel gives you the exact day and time of day when those occurred. So it helps you identify not only the problem itself, but when it occurred, which is quite useful if you're trying to track down problems. The upper right blue panel would show you the time series if I had them available. I don't have them on my disk, so I wasn't able to show it, but that would show you the time series. So you could do a comparison between the spectra and the time series, which helps. At least I like to see both, just to get a sense of whether it's a real event or not. Most likely this is a data gap. Usually when there's a data gap, there's a zero fill, and so that step in the time series, if you take an FFT of that, it's a straight line across in the PSDs. Okay, so that's just another feature of the SQLX, PQLX software that you can take advantage of for doing QC. And again, this software is designed more for a QC analyst. It's not so much a research tool, but although it can be used for that, mostly it's used by network operators for doing sort of routine QC on their data. At the USGS in Golden, at the National Earthquake Information Center, we would run every day. We would run the data, run the previous day's data, and we could have a look and see how things were changing day by day. If things were going off, problems were occurring, or if things were just cruising along and working well. Okay. Again, SQLX, like I said, I think you guys have a license for it. It was developed and is currently supported by Richard Bose. So if you guys need any work on that, he's available to work through Nanometrics, I believe. I'm not sure how that arrangement works, but he wanted me to let you guys know that if you need any help with it, he's available to do that. But you'd probably have to go through Nanometrics through your original license to figure out how to make that happen if you'd like to keep working with it, or if you'd like to expand the functionality somehow. Okay. And finally, let's go through and talk about OBSPy. It's a Python library that where you can also plot these power spectra plots. And the advantage of that is of Python, as opposed to the Mustang example that I showed you, is you can run it on any data available through an FDSN wave server or any data that you have on your disk. It's a standalone library that you can apply to any data that you have. Okay, unlike the Mustang, which is pre-computed PSDs at the IRIS Data Management Center, and you only can view the stations that they have in the system. PQLX, SQLX, and OBSPy all allow you to investigate data that you may have on your disk or data that's available through an FDSN server. The OBSPy is a lot more limited. It's not like PQLX or SQLX. It's not an interactive system. It just allows you to grab some data and compute a single plot. And I'll show you an example of that. This is the website, the OBSPy website for the power spectral density function. It's called PPSD, probabilistic power spectral density. And to the right here, I just showed an example of what one of those plots looks like. And I'll go through in a little more detail. This is just the, what I've shown here is just the example that they have on their website. Again, you can go and look at this. It gives you examples on how to run it. It's pretty useful, but again, it only creates static plots. It doesn't have the interactive functionality of something like SQLX, okay? Let's go through. What you need to do for that package is install Python. The OBSPy folks recommend Anaconda Python. It works well with OBSPy. And here I've included the...
We have to install Python 3, or we also can use the Python 2 version.
It should work with Python 2. I have 3.8 installed. I think I used it with Python 2 as well. I think you froze up. Can you guys still hear?
Halo Pak Supri.
Okay. Looks like everybody froze up for a little while. Can you guys hear me?
Yeah. Okay.
Yeah, we hear you fine.
Okay,
Yeah.
great. So it would be interesting to see if you can run this with Python 2. Do you have OBSPy installed?
Yeah, I think we want to talk to the participant to install the Python maybe before the third day of the training. Yeah. So
Okay.
you recommended is Python 3. Yeah.
Yeah, I would recommend installing the most recent Python
Okay.
3.8. It would be interesting to see if Python 2 works though. We could try that. I could give you the script and you could see if it runs. But basically there's 3 steps that we could go through tonight or over the weekend to be ready for next week. Step 1, install the Anaconda Python package. Step 2, install OBSPy. And then step 3, we can run a script that I've written and can make available to you. So again, the installation of Anaconda is shown here. The website is at the top here. And so we can, if you want to go there and grab the very first blue line here, install Anaconda following the instructions on their site, that's where you go to get the right version for your operating system. I have it on a Macintosh, but it also runs on Windows and Linux. So you can go and do that. And then you can install the precompiled OBSPI package as well. Conda install OBSPI is the command. And so I'll make these slides available to you. I'll send them to Walter tonight or tomorrow morning. And you can work through these and try to get it installed if you'd like. The next slide, here's OBSPI. It has tutorials, it has descriptions of all the different features. This PPSD function that I'm talking about is only one of many other functions that you can use in the OBSPI package, but that's the only one I was going to talk about tonight. Okay, so and then finally, this is the PPSD web page. Tells you all the different flags that you can set, the ways you can look at it. You can add statistics to the top of the plot. You can change the color bar, other things like that. Okay. So again, all of these, you can go through all of these in some detail if you'd like, or we could let you guys have at it for a few days and revisit this next week if you'd like. And then finally, here's the script itself. This script will produce the plot to the right. This is again for station GSI. Once you get Anaconda installed and you get OBSPI installed, you should be able to run this script. And all it does is it goes to the Geophone GFZ FDSN server. It grabs the data. I only selected 3 days. If you look at the plot to the right, you can see that it's May 13th to May 15th, 142 individual data segments, and it produces the plot for just those 3 days. It grabs the data, removes the instrument response, and computes the PSDs and plots them in the PDF distribution. All of that with just these few lines of code. Okay. I've kind of confused it a little bit. I have this in frequency as opposed to period, but that's just a flag we can set. I can show you how to change that. If you look at the script there to the left, you can see where some of the things you have to bring in. You have OBSPI clients, you have matplotlib, some of the other libraries that you bring in. You can set the FDSN client. GFZ is the other one you can use is Iris. Those are the two standards. I'm not sure of the others. I know there are several others, but those are the two that I've used most frequently. And then the station I set to GSI. And you see the next lines down. It has the net code, the channel, the dates, the date range, and then it goes and it gets the waveforms, it gets the metadata, and produces the plot. The main function down here is towards the bottom called ppsd.plot. That's what actually produces the plot. So if you'd like to, again, I'll make this available through Walter, and we'll see if we can get this to work if you'd like. Okay.
That'll be great. That'll be wonderful.
That is really all the slides I have tonight. There's a lot of information on all those. So if you'd like to launch off into questions and have a discussion, that would be great. Or I'm pretty flexible. Whatever you guys want to do.
Well, have a look in the chat box. There's some questions already.
Okay.
Yeah.
Okay.
Yeah.
Let's see. Should I start? Where should I start?
Maybe I can read the question. I'm sorry.
Okay.
Okay. The first question from Nesia from Balai Satu. She asked about how can we identify the waveform of the earthquake in one day by looking the spectrum issue based on the NL, NM, and NH and M. That's a question. Please.
Well, I chose this day for the OBSPI example because it has an earthquake in it. Can you see my screen still if I'm not?
Not yet.
How about now?
Oh, still the same. Not yet.
Am I
Do
sharing?
you share something, Daniel?
Here, let me try again. There. Should be able to see my screen again. Can you see that, the script?
Yes. Yeah.
I chose this 3-day period as an example at GSI because it has an earthquake in it. You can see the very high power. If you look at the PDF plot to the right that's created from this script, the very high power light pink line that goes across the whole top of the plot there, that is a magnitude 6, I think a 6.4 earthquake, maybe a couple hundred, maybe 200 kilometers away from the GSI station. So that's one earthquake, and I think that answers the question. How can you identify the earthquakes? They are generally these high power, very low probability, but high power events that go well above the rest of the PSDs that are representing the ambient noise. Below that, you can also see some individual surface waves, maybe, or the very light pink lines that pop up near the high noise model. Those are probably also little earthquakes. I wish I could. I'm not able to get my cursor to go over there. But anyway, those are the earthquakes. Does that make sense? Does that answer the question?
Yeah, I think enough. I think your explanation can answer the question.
Okay.
I have question on the left side. You can see the script.
Yes.
When we about the how to plot the PPSD, there are I think there are so many parameters. Maybe you can explain, like especially for the part PPSD.plot, you can explain one by one the meaning of each parameters in the script. Please.
For the PPSD plot command,
yeah,
specifically.
Yes, for example, for CMAP, what is the meaning? CMAP means
that's the color map. Yes.
Okay.
Yes. So there's a color map, and it's called PQLX because it's the same color scheme used in the PQLX software. There are other color map choices that you can make. If we go back to this page where it shows all of the different flags that you can choose, you can see CMAP is down near the bottom, and there are others that you can choose. I don't see, you'd have to click, if you're on the website, you could click on that hyperlink, matplotlib colors color map, and it would give you other choices. There's a black and white, there's a jet. So you can change the color with that if you get tired of all the pink and purple. Yes, so the other one just to the left of that, x-axis underscore frequency equals true. That's how I changed it to frequency. If you put false there, it would be in period, for example. Okay.
Okay.
And then the next one, moving to the right, period underscore lim. That's where you set the x-axis, 0.001 to 10. That's the frequency range of the plot. And then show false. I'm not sure what that is actually. Show false. Let's see. What did I do there? Show mode. Show enable, disable immediately showing the plot. Okay, so that's just to show it or not in the terminal in a separate window, I believe. So
okay.
Yeah.
I have question. Another question.
May I?
Okay.
May I?
Oh,
ask?
Pak Jamroni.
Jamroni,
Okay.
Pak. Yeah.
Pak Jamroni, silakan. Okay, please.
Okay. Thank you, Daryl. In South Sulawesi, we have a key API station.
Mhm.
I don't quite understand about how to get the data for 2 years, for example, in key API station, because as far as I know, I have never get the data and process like that. How to get the data and the process with borehole, kemudian posthole, how to get this data and processing like that. Thank you.
This is using this example here that I showed. This is using the Mustang system. And
Yeah.
so this is the web page. If you to the left side shows a view of the web page. So if you open up a browser and just search for Iris Mustang noise PDF, you'll get this page. Actually, you'll probably get this page. And then if you look to the upper right, there's a button that says URL Builder. And if you click on that, then it'll take you to this page where you can enter the station that you would like to look at. If I can, let's see if I can show an example. Can you still see my my screen?
Yeah.
So this is the Iris Mustang noise PDF URL builder. If I type KAPI here, BHZ, it creates a URL down here at the bottom that if you click on it, it will build the PDF plot for the station that you've selected.
Sorry, Daniel, we cannot see your web browser. We
Oh, no?
still see your presentation.
Okay, let me try to share again. Maybe I have to reshare it. Here we go. Can you see my screen now?
Yeah.
Yeah.
Okay, so let me start over again. If you were to do a search for the Iris Mustang, you could just do a search right here for this string that I've just highlighted, Iris DMC Mustang noise PDF, and you should get to this page. And then this here, if you can see this button, that's the URL builder. You click on that and you can type in network GE station KAPI. Let's say 00 location code, BHZ. We can do a long period of time. Let's try 2010 0101 to 2021 09. What's the date today? 22, 23 where you are, right?
Yeah.
And then if we click on this URL, see how long it takes. Oh, it didn't work. Ah, of course. Maybe it doesn't have that much data. Okay, here we'll make a plot. Let's change this to 2015. Change that to 20. See what happens. GE. Oh, I know why. I'm sorry. I got the wrong net code. It's II. It's the, I'm sorry, I'm mixing net codes. So the net code is II, that's Iris Ida. That's the Global Seismograph Network. Station is KAPI. And we chose, let's go from 2010 to 2021. See if we can do it. It's 11 years worth of data that just plotted out that quickly. So that is a lot of data. And so that you can see it's a pretty good quiet station. So does that answer your question? Is that?
Yes, yeah. Okay, thank you.
That's where that came
Yeah.
from.
Thank you.
Daniel, there are several questions in chat box. Maybe I can
Okay.
the question from Pak Supri itself. He asked about how what is the data format that we can use, whether we need seed or other. And the second question, how about the time consuming needed to compute the PSD? Is it need high specification of the computer or laptop? That's from Pak Supri.
What is the data format and what's the time to compute the PSDs? Is that the question?
Yes, data format that can just to generate the PSD.
Well, with Mustang, it's all pre-computed, so there's no data format. Are we talking for the PQLX, SQLX code? That can use mini seed. It can run on SAC. Couple other formats that are specific to strong motion data. I can't remember, CDSM, something like that. That's the waveform data, but it can also, for metadata, it can use station XML, RESP files, or full seed, I believe. So that's what you need to compute the, and that would be, here's an example of, I've got SQLX running right here, actually. Here's one of your stations, one of the geophone stations, PMBI. Can you guys see? Let's see, I need to share it. I'm sorry. I'm getting kind of ahead of myself here. So what, can you see my screen again?
Yeah.
So this is SQLX running, and what I did is I downloaded from the GFZ FDSN wave server, I downloaded data in mini seed format, and then I downloaded the metadata in station XML format, and then I run, there's two parts to the SQLX. There's a server that runs to compute all the PSDs, and then there's this, the client viewer, where you can then look, interrogate the database and pull up different views. Okay. Is that, I hope that answers the question.
How about the specification, as mentioned in the second question? Specification of the computer that can be used or sufficient enough to use this applications for SQLX maybe or PQLX.
For the SQLX, I'm running it on a Linux virtual machine. It's in the cloud, which is why it doesn't really run that fast. You can run it on a local Linux machine or a Mac. I think it also runs in Windows. I'm not exactly sure about that. I could check on that with the developer, but I know you can run it in Linux and on a Mac. I will verify if you can run it on Windows or not. But it should be, the more powerful the machine, the better, and the more disk space you have, the better. Then you can store a large database and have a lot of waveform data available for processing. Okay.
Yeah, enough, I think. Thank you very much. And then for the another question from Titi Lestari in Skal, she asked about we use the LNM and HNM frameworks of the Peterson model. Are the data from all types of seismometer, including data from short period seismometer, ideally within these limits?
Oh, for weak motion sensors, yes. For strong motion sensors, no.
Oh,
I can go back and show that example again that was in my talk. Let me share my screen again, and I'll make this full screen. So let's go back. Here's the example that I showed. I'll just talk about it a little bit more. So in both of these panels, you can see the gray lines for the high and the low noise model. The upper panel is the weak motion vertical component at KAPI. It's station or channel BHZ. Again, this is 6 years worth of data from 2015 to 2021. And you can see that a vast majority of the data is within the low and the high noise model. The bright green colors are higher probability, suggesting that that's the level of the station when it's at rest. That's the ambient noise level. Anything above that or above the high noise model will be an earthquake, like I showed in the other examples. Can't really see too much because it's very faint. But if you go down to the next panel, that's a strong motion sensor. And those are the noise floor of the sensor is so high that it's well above the high noise model, okay? All these bright colors represent the lowest level that can be recorded by the sensor. So you don't see the ambient noise levels, you don't see small earthquakes because the floor of it is already so high. You only see large earthquakes, really. It's kind of not a very good plot, but that's what it looks like. So the answer to the question is the high and the low noise model were developed for weak motion sensors, not strong motion sensors. Okay.
yeah.
Okay, thank you, Mr. Namal.
Thank you.
Okay, terima kasih Bu Titi. Another question from Pak Supri. Is the noise still high if we put strong motion sensor? Why the noise still high if we put strong motion sensor in bedrock or silent place?
Well, there's kind of a different philosophy with strong motion sensors. Those are meant to record strong motion from a strong shaking earthquake. And so it's kind of interesting. With broadband weak motion sensors, we want quiet stations so we can record distant earthquakes or small P waves to locate the earthquakes. With strong motion, we really don't care about the noise characteristics. In fact, we want to record the soil characteristics. So putting them in the shallow ground so they record the strong shaking and the site characteristics that a building might experience is more what you're trying to record with a strong motion sensor. Does that make sense? So oftentimes at the USGS, we'll have a strong motion sensor at the surface in the shallow soils, and then a weak motion sensor down in a post hole or a borehole. So it's in a quieter environment. So there's two different things you're trying to record with the two different types of sensors.
Okay. Yeah. I have my own question about the noise. As we know, especially for the broadband sensor, is highly affected by by the condition of atmosphere variation, such
Yeah.
as rain, maybe air pressure or winds, and how to analyze from this PSD.
Well, I think that's what's going on here in the diurnal plots that I was showing before. If you can see this plot still, this is from SQLX, a view of your station GSI. And so the horizontal components at the long periods are very unstable, and they have this strong variation throughout the day where they're noisy during the daytime hours and quiet during the nighttime hours. And that's probably due to thermal and atmospheric pressure variations throughout the day, exactly what you're talking about. And those pressure variations can cause tilting of the vault that the sensor is in. If there's sun hitting the vault, it'll cause instability. So for these weak motion sensors, it's really important to get them into the ground, get them insulated and isolated from the heat and the cooling and the atmospheric pressure changes. Okay, does that answer your question?
Yeah, brief
Yeah,
explanation.
Daniel, can I ask something?
Yes.
From this presentation that you saw that the diurnal variation plot, why the PSD only use 48 PSDs?
Oh, I think that's a little
What's
bit
the meaning?
misleading. Yeah, that's just the number of hourly plots per day. So there's two averages per day. If you look at the PDF plots to the left, you'll see that it's actually made up of over 44,000 individual PSDs. But then for the diurnal plot, it's two averages per hour.
Per hour.
Yeah.
Because when you from the other slide, you saw 52 PSD. For the same
52.
station.
Yes.
I see that.
That's just the number of averages
that using for this analysis.
Yeah.
Okay.
Yep.
And what's
But
the meaning
again,
what's the meaning with the pink color below the low model?
Those are similar to what I showed in this example here, where you can, that's probably a dropout where you might lose a packet or a short section of data. And so usually systems will fill those gaps with zeros. And so you'll have a step function in the time series. And when you take a Fourier transfer of that step function, it'll be a straight line across.
Okay.
Does that make sense?
Yeah. And can we define the earthquake PPSD from the PDF from this ping diagram?
Yeah, there was one example where I think the example I showed this one here has an earthquake in it. I specifically chose this 2-day period to show you an earthquake. So if you look at this panel, the PDF to the right,
above the high noise. Okay.
Yes, the high level, the highest level lines, those are earthquake. Yep, exactly.
Okay.
I'll show this in a little more detail on next Tuesday morning for you. I looked it up. It's a magnitude 6.4 earthquake, I believe, just a couple, maybe 100 kilometers from the station, maybe 200. I can't remember, but I did make an example of that we can talk about. So you can see pretty well that this station is pretty quiet and has no problem recording. If you look lower down though, the next line is, say, look at the 1 hertz level. There's the high magnitude earthquake. I wish for some reason my cursor will not go over there, so it's not easy to point to. But if you go down lower, those lines, the light pink lines above the high noise model, those are more around magnitude 4. And so you can see the difference in the amplitude of the 6 and the 4 and how that is related to your ambient noise level.
So the two highest is 6, and then below it it's 4 magnitude.
4, yeah.
Yeah,
Yep.
in the 1 frequency, 1 hertz frequency.
Yes, exactly.
Okay. Thank you.
Yep. I can show. We're getting ahead. This is going to be in the next week, but that's okay. You guys have good questions. Okay.
Okay, maybe some question from Rahmat Bilianto. He asked, can Mustang PKLX SLX can process accelerometer data too? But you already mentioned the accelerometer data cannot be used for the PSD, right?
Well, it can be used. I mean, how do I phrase it? You can definitely process strong motion channels in SQLX. But I just meant to say that you can still use SQLX to do quality control on it. The only point I was trying to make is that the strong motion channels look very different. They're very high, and you won't see any of the ambient noise. Here, let's go back to this example. This is a Mustang example, but again, you can see it'll look the same in SQLX. So you'll see very high. The lower panel is the strong motion channel, and the noise floor is so high that you won't see anything below that unless there's a problem. You can see light, faint lines underneath that very thick line, and that might indicate that again, you're having data dropouts and things like that. So you can still use it for QC. You can still use it to see if you're detecting earthquakes, things like that. So it still could be useful to use SQLX on these channels, I think. And I can show you some examples. I'll try to process some data and maybe do a little more of a demo with SQLX next week, if that would be something you'd like to see.
Okay. Thank you.
Yes.
Okay. We can move to next question from Muhammad Reza. He asked, can I see PDF result sample on Accelero? You already showed the PDF. And how to determine high noise model and low noise model for PDF on Accelero? Yeah, but you already mentioned, right? You already answered.
Well, there's a paper out by John Clinton maybe 10 years ago where he made high and low noise models for accelerometers, strong motion sensors. They just haven't been integrated into PQLX or Mustang. Nobody's really using that yet, but that's something that would be useful to do, is to show the high noise models and low noise models for the accelerometers as well. Just haven't done it yet. I'll bring that up with the developers. I don't know quite what that would show. But since we're not really looking at ambient noise, you're only looking at the noise floor of the sensor, and then large earthquakes that are strong motion earthquakes that are being recorded by the sensor. Okay.
Okay. Yeah. In Bmkg, we we also use beside the broadband, we also use short period sensor. How to set up the right or correct period limit in Xscale, maybe, and how to know to set up
For SQLX or OBSPI, I'm not quite sure what you're asking. I think you can process those as well. I've definitely used SQLX to look at short period sensors. They just don't look like the broadband. They'll be very, limited in their frequency band, but you can still use the software for quality control. No problem.
Okay, thank you. And then for the next question from Bu Titi Lestari Inskal, she asked, to form a PSD file from seismic data, we need the response file, I think, data
Yes.
from each seismometer component. How do we get the response file data?
Well, in the you can get it from the IRIS. If IRIS holds it, you can get it through the metadata aggregator. This is a useful. I'm not sure if I'm still sharing my screen or not. Let's do this.
Not yet.
There's a nice website that IRIS operates called the metadata aggregator, and you can drill down into different stations and by channel go and find the metadata that's available. Here's, for example, the response transfer function for this particular channel. And I believe you can grab it as a RESP file or a station XML. Here it is. Here's the, so for this particular case here, you can click and here's the station XML file with instrument response and all the metadata. Here's a RESP file. If that looks familiar to anybody, that's what I'm most familiar with. So you can, if IRIS holds the data, you can get it, you can find it. I believe also they have metadata available for stations that they don't operate. For example, we can look and let's check a geophone station here. The fan on my laptop is going, must be working hard. So here's the here's a station in Indonesia, geophone station at Bkg in Sumatra, and we can go in here and do the same kind of thing. Here's the RESP file for that station. So you must have supplied this to IRIS at some point, I imagine, your organization. So that's where you would get metadata for stations that IRIS has in their archives. Is that, I'm not sure if that answers the question or not.
Ya. Ya. Gimana Bu Titi? Sudah bisa menjawab?
Iya, thank you, Mr. McNamara.
Okay.
Maybe.
Yeah, thank you. I think enough the explanation. We can move.
The other way to do it.
Okay.
If we go down, let me just one more quick comment. The other way you can do it is through the Python script that I've shown here. This was the last slide in the presentation that has the Python OBSPI script. There's a command in here called FDSN service get stations. It's about halfway down the screen. And that, you can see at the very end, it says level equal response. That gets the instrument response also from the FDSN server. So it pulls the response, and then the next command is get waveforms. And so with those two commands, you have the instrument response and the waveform to compute the PSDs. So that's another way you can get instrument responses from an FDSN wave server. Okay.
Thank you. Maybe we can move to next question from Pak Ridwan Kusnandar. He asks, in OpsPy, can we combine PSD of each component, ZNE or station? For example, 10 station, 6 station in one chart. Please.
Ooh, I don't know. That's a good question. I don't know the answer to that one. I would say no, but I don't know. I could be wrong. I'll look into that though. But I think probably no.
Okay.
Okay.
Oke. Gimana Pak Ridwan? Apakah cukup penjelasannya? Mungkin ini kalau yang di chat sudah habis ya, mungkin bisa langsung bertanya ke Pak Daniel,
Yes.
rekan-rekan sekalian. Maybe the participant can ask directly. Any question? Yeah, maybe I have a question, Pak Daniel. About the instrument response. You explain about the FD iris or maybe what kind of format of the instrument response. This particularly for this example. What format? As I know, there are several formats, well-known formats such as station XML or dataless format.
Yes. So at Iris, there's 3 different formats. Here's the. Is that what you're asking at Iris or? Okay. Yeah. So here's that station BKNI again. When you go down here, it's pretty well hidden. I wish they made this more prominent, but you go down below the plots that show the phase and the response. You have 3 different selections. You can get the instrument response as a RESP file here. Am I sharing my screen?
Yes, can see.
You can see it?
Yeah. What the meaning of what you mean? Which screen? I see the response chart here for the KNE.
Yes, that's what I was hoping to share. And then the other one is the old SAC poll 0 format that you can see here. And then the third is the XML, which is the more modern standard way to store metadata. And you can see as we scroll through, it has the poles and zeros defined. It has all the FIR filter coefficients here down below. So there's 3 different forms. The station XML probably has the most detail. The SAC pole 0 file is pretty simplistic, but it covers the total response without really covering the digitizer and the FIR filter coefficient, stuff like that. Yeah. So yeah, I would. But also, again, the RESP, there's a RESP file format that has all the coefficients in it as well. So you can get those from Iris. You can do it through the web like this, or you can do it programmatically using Python or wget, I believe is another way to do it. So does that answer?
Yes. And I have question in Bmkg, we use SysComp3 for the earthquake processing, and then we familiar with for the metadata for the response file, familiar with SysComp3 response file format. And when we want to use or we want to generate the PSD using PKLX or SKLX, we use the SysComp3 format, or anyway, or we have to convert it to Iris format, or supported another supported format?
My understanding is that SysComp P3 uses station XML. Is that not
Yeah,
true?
station XML. Yeah.
Yes, that's fine. SQLX can input station XML. The only thing I can think of is that I believe that SysComp P3 only uses the most recent epoch. It doesn't store the historical epochs. So if you want to do older data, if you want to run older data through SQLX, you'll need to get the historical epochs. Does that make sense?
Yes. Yeah. Thank you.
That's my understanding of SysComp. Just for speed and efficiency, they will only use in the real-time system, they'll only have the current instrument response epoch.
Yeah.
Okay.
Okay.
But yeah, station XML is fine for SQL, no problem. That's what I use. That's what I've been using to process your data.
Januar masih boleh nanya?
Ya, silakan Pak Jamroni, please.
Okay, thank you, Daniel. I have a question about OutSpy and Anaconda. I have installed Python 3.8, but
Yes.
I don't know how to conda config or OutSpy in Python. Is it any manual or practice in this next workshop?
Yeah, I would go to this page that I have. I'll make these slides available. I'll send them to Walter and he can send them out to you guys. But I would go to this. Let's see, am I still showing my screen? Can you see my screen?
Yeah, response file.
Now you should see installation via Anaconda.
No, still response file.
Okay.
We should stop sharing and then.
Yeah, I'm trying to find that. Let me see if I can. Not sure why I cannot get back to. Let's see. Sorry, everyone. I'm not sure how to share my screen again. I don't see the buttons to do that. I'm sorry, I don't see the.
Do you need to unshare and then reshare?
Probably.
Stop
Oh,
sharing.
here it is. I'm sorry, it was on my other monitor. I have two monitors and I wasn't looking on the right one that time.
All right.
Thank you. Okay, I'll share screen again. I believe it's this one. Okay, can you see OBSPy?
Yep, we see it.
Anaconda. Okay, I believe the answer to your question is here. Installation via Anaconda. This is just a screenshot from the Anaconda website, or from the OBSPy website, where they recommend the Anaconda installation. So if you work through this, you should be able to get through the Anaconda and the OBSPy Conda package install. Okay. You can just do a Google search for OBSPy Anaconda GitHub, and you should be able to find this page. Otherwise, like I said earlier, I will make this available. I'll send it to Walter and he can send all the slides out to everybody and you can work through these commands. but you should be able to find this on the web fairly easily. And the website is actually at the top of the page here, GitHub, OBSPy wiki. So if you search for that in Google, you should be able to find the installation page. Okay.
Daniel,
Yes.
so far you have explained how to install OBSPy, particularly. Maybe you still not explain how to install maybe PKLX. Maybe you can explain how to install PKLX.
Yes,
Because very useful.
that's fairly lengthy. That's a pretty lengthy process. There's a manual that I wrote many years ago in 2010 that explains it in detail. You need PQL2, which is a binary that you can download from Iris. That's the first code, and then you install PQLX on top of that. But you also need to install the MySQL database system because it makes use of that. And so there's a lot of dependencies and a lot of things you have to install that's all outlined in fairly good detail in this document. What I would recommend, since you have a site license for SQLX, see if you can do the SQLX installation, because that all comes as a binary with everything already packaged together. And you just have to install a code called the Docker and then bring it in through the Docker, and it will install the binary. So that's what I would recommend, going with SQLX if you guys have a site license and you're able to do that. And I would need to check with Nanometrics to see what the details of your site license are. The PQLX, as I mentioned, it's kind of old. It's 10 years old now, and it has a lot of requirements. And I don't even know if it still is compatible with MySQL, for example. So that's something I would need to verify. Okay.
Yeah.
If you really want to know the gory details about how to install, then download this open file report, and I'd be glad to go through it in detail, but I don't know if we have time tonight. It would require maybe sitting down in a room together and working on it all day. It's fairly involved.
Yes, yeah. Because PKLX can be useful for maybe someone who wants to use a PSD for private use, maybe for individual personal research,
Yes.
maybe.
Yes.
Okay, thank you very much. And I think Pak Supri punya Pak Supri has another
Excuse
question.
me. Yeah.
Pak Supri, silakan.
Okay, Daniel, can you show the slide comparison of the Trillium 3060 and Trillium 120?
Yes, I think I had an example of that.
The question
Yes.
is it in the similar location? The first one,
Yes.
the first question. Is it in the similar location?
Well, this example here, I think I understand your question. Let me see if I can answer it. This example here, station KAPI, has a Nanometrics Trillium 360. The upper panel is the 360, and you can see the very low noise that tracks along the low noise model. That's the 360. It's a very good sensor. The panel below, the LHZ in the lower right, that's the Trillium 120. Has slightly higher noise, especially at the longest periods. It's a little bit hard to see because the plot scale is different, but you can see the the scale on the side, it looks like the 360 is about 10 dB quieter, 10 decibels lower for the ambient noise level than the Trillium 120, which is not that significant. But it does have better long period characteristics just because of the long period corner. You can see, it's kind of hard to see in this plot, but the 360 actually resolves that hum at 100 seconds as opposed to the Trillium 120 that does not. So it's slightly better. The 360 is slightly better, but really not significantly better, such that it would have an impact on your ability to use the long periods for earthquake products. They both look fairly good. Okay.
Okay, thank you. One more question, Daniel.
Yes.
If using the PSD method, what is the longest and also lowest period that we can still analyze?
I'm sorry, what is the lowest
period and also the highest on the highest frequency and the lowest frequency that we can still analyze?
Well, the lowest frequency, I'm sorry, the highest frequency is going to be a function of your sample rate. So the Nyquist frequency is half of your sample rate. So if for the data here, for the GSN, let me think about this. So for this example, let's see, let me show a GE station. The geophone stations that I was looking at only have 20 samples per second. So when you look at this panel, for example, the upper row is station GSI. This data is only 20 samples per second. So you can only resolve about slightly under 10 hertz, which is about 0.1 second period. So you can see that these graphs all cut off on the left side at about 0.1 seconds. So that's the highest, that's the lowest period, highest frequency that you can resolve because of your sampling rate. If you want to go to higher frequencies, you have to have a higher sample rate. This is the GE data. The GSN, the global seismographic data that I was looking at, that I showed examples of, let me find an example. The II data. Here we go. This data is 40 samples per second. So you can get out to about 20 hertz is your highest frequency that you can resolve. Okay. So generally the Nyquist frequency is half the sample rate, and that's about the highest frequency that you can resolve. On the other end, the long period, that's a function of the time window, the length of the time window that you use to compute the PSD. Generally, if you want to resolve a certain period, you have to have a time window that's about 10 times longer than that period. So if you want to resolve 100 seconds, for example, you need about 1,000 seconds of a time window. For most of these examples, I'm using a 1 hour time window, which is 3,600 seconds. So we can resolve with these plots, we can resolve out to about 300 seconds period. Does that make sense?
Yeah.
So on the high frequency end, it's a function of your sample rate. On the long period end, it's a function of the time window, the length of the time window that you use to compute the PSD.
Okay. Thank you. Very clear, Daniel.
Yeah. continuing Pak Supri question. Yeah, how about the short period seismometer? As we know, short period has for the low frequency, it can detect or record only for the lower limit about 25 seconds. How to make a limitation of the scale.
Oh, okay. Well, that wouldn't be, if you do it in SQLX, it would be automatic. If you do it in OBSPy, you can set that limit in the script, for example, that I've included. In OBSPy, here's the script on the left side. If you go down towards the bottom, there's a command called ppsd plot, and in that there's a flag called period lim, and that's where you can set the x-axis range. So if you had a short period sensor, you would want to change that to reflect the spectrum that you have in the data. But if you do it in SQLX, it will automatically scale the plot for you. And there are some ways to do it. If you don't quite like the way it's done automatically in SQLX, there's a control button and where you can go in and set different parameters. Okay. I think that answers the question, at least for those two different codes.
Okay, thank you very much for the answer. Any question from the participants? If there is no silakan Pak Bambang. Oh, okay. If there is no another question, maybe I'll return the session to Pak Supri to close the session.
Thank you, Pak Yanuar. I think we hope that any comment from Pak Walter.
Well, I'm very encouraged. These software tools are not really difficult to use once they're installed, and I'm very encouraged that Bmkg can use them to evaluate the stations. And I'm hoping that people in each region, not only in Jakarta, but in Bali and in Sumatra and Sulawesi, will try to use these software tools. Thank you.
Okay, thank you, Walter. I think I want to say thank you very much for the Dr. Daniel McNamara and also Professor Walter Mune for this excellent training today. We will continue the third day on the 28th September.
Great. Thank you very much. It's
yeah,
quite enjoyable.
Yeah, okay, thank you very much. And on the participant, you have to make the little resume of this course. And you can collect the resume in the third day, and also maybe some of the exercise in the third day training. Thank you very much for today's training. Good night for Walter and also McNamara. Thank you for all of the participants. Thank you.
Have a nice sleep then.
Thank you, Daniel.
It's already late.
Thank you,
Walter. Thank you, Daniel.
Bye.
Terima kasih
See you
semuanya.
later.
Next week.
Kasih Pak Januar.
Terima kasih Bu.
Mungkin untuk teman-teman tuh bahasa Indonesia aja Pak, repot amat.
Iya, pada keder kayaknya.
Biar latihan katanya Bu.
Oh iya benar juga sih.
Iya. Yes.
Thank you, everyone.
Thank you.
Yeah, good night.
Thank you.
Bye.
Terima kasih.
Bye.
Good evening.